Give him an applause, come on.
All right, good morning, everyone. My name is Milko. I'm going to hopefully be able to talk about fibers this morning. So it's about asynchronous programming. So how this is going to go down is we're going to quickly say what fibers are about. We're going to take a look at the class, do a quick demo, and then we'll have to dig into how to actually use them because they're rather useless on their own. So let's begin. So PHP fibers. PHP fibers are a thing that landed in PHP 8.1. And what they allow us to do is that they give us tooling for better asynchronous programming in PHP. And for me personally, this is really exciting. I was wondering when is PHP going to get something asynchronous, and if at all. And I actually asked this question once at a conference, like, are we getting anything asynchronous in PHP, like something like async, await, or promises, or something like it? And the answer I got is, well, we got generators. So generators allow us to do asynchronous programming, so what more do you want from life? But yeah, indeed, we can use generators for asynchronous programming via a bunch of hacks and a lot of boilerplate code because they were really not designed in particular for this kind of asynchronous programming, which async and await gives us in other languages. So yeah, it didn't really make me very happy. This answer didn't make me very happy. And suddenly we got fibers in PHP 8.1. And I think this is the coolest way to do asynchronous programming. I think this is the right way. Single-threaded asynchronous programming. So let's see what it is about. Slide number 1, that's me. I'm a developer, full stack contractor. I'm currently head of development for a startup called MySupply. Organized the conference once, and if the whole COVID thing goes away, I'll do it again. And so fibers. What fibers can do for us is they can execute our code. They can suspend their own execution at a particular spot. It's up to the code that is being executed by the fiber, in the fiber, to decide whether this will happen, like whether the suspension will happen or not, and when, if it is. They can be resumed once a fiber is suspended, once this code has stopped working. It can be resumed from somewhere else in our program, something that holds reference to this fiber. When you suspend a fiber, it can spit out some value for usage outside of the fiber. And then when you resume the fiber, you can inject some other value in it. So this is basically it. As Derek said, this resembles Windows 3.8 multitask, well, not multi-threading, but multitasking. So this is basically, you start some sort of a task, you run some sort of code, and rely on this code to at some point pause for whatever reason and give control back to something else. So that this something else can do its thing, and then hopefully the something else will resume the code that stopped. We'll have a little bit of a demo to make this a bit more illustrative. A fiber is represented by a class in PHP. So the API to deal with a fiber is a class. This class, in its constructor, we pass a callable. The callable is the code that we want to execute in this fiber. The class gives us a start method, and the start method will start executing the code. And when starting, it will pass the arguments that has been passed to the callable. It has a resume method, and this will resume executing the fiber in case that the fiber was suspended. It has a throw method, which we can use in order to throw an exception from within the executed code. We have is started, is suspended, is running, and is terminated. So is started, I think, is pretty self-explanatory. Is suspended as well. Is running. God, I forgot what this flag was about. And is terminated is telling us whether we reached the end of execution of the callable that we passed. Get return value, or get return, sorry, will give us the return value of the function being executed in the callback. And those two here, get current and suspend, those are very important because those static methods allow you to get a reference to the fiber that is currently being executed from anywhere down the stack. And suspend will allow you to suspend the fiber from pretty much anywhere. We'll talk about this a bit later, but if this seems like something very similar to what a generator does and looks like, it's because it is, but the very big difference is those two static methods. Because the get current and suspend allow us to stop the execution of whatever's being executed in this fiber from wherever in the stack. Well, a generator can suspend itself only at the level at which the generator is. So if we have a generator function, which has a yield somewhere inside itself, it will suspend. But if the generator function calls another function, the called function cannot suspend the generator that called it. So, yeah. Just for the sake of completeness, there is a reflection class that comes for the fiber. We don't really care about this too much right now, so we won't focus on it. There is a reflection class for the fiber class. So let's check out what we can do with a fiber. So we'll define a function. Oh, here those 5 lines of code. It will just echo stuff and it will suspend. So what it will do is it will echo this is fiber and the name that we passed awaiting to be resumed. Then it will suspend itself, like here. And then when it gets resumed by something else, it will continue execution here. It will echo name is from the input. This is what we get from the input. And it will return whatever we passed. So we're going to create 2 fibers, F1 and F2, with the same function. And we're going to start execution of fiber 1. We're going to pass in this parameter here, Optimus. And what we'll get is this first line of output. This is fiber Optimus awaiting to be resumed. That's it. That's what we're going to get, only the first row. Then we're going to start the second row, call it Megatron. And this will split out the second line. This is fiber Megatron awaiting to be resumed. And then we'll come back here. And then we're going to echo F1 was suspended with, and we're going to get the result of this. Get this line. F1 was suspended with Optimus. This is what we code the suspend with. And F2 was suspended with Megatron, because this is what we're getting out of the output. That's fine. Not very interesting so far. What we're going to do is switch the order of execution now. We're going to start with the second fiber that we instantiated here, and we started second. We're going to resume it with bad. Execution is going to come here. Megatron is from the bad guys. And then we're going to come back here. The function will return, get back here. We'll resume then the first fiber. Optimus is from the good guys. And then I'm going to get back here. We'll echo fiber 1 returned Optimus. Fiber 2 returned Megatron. That's it. That's all about fibers. Not really exciting, but pretty much that covers it. It gets a bit more interesting when you try to nest them. Well, you don't try, you get to nest them. So you can nest fibers. So you can start a fiber from within another fiber. That allows us for some pretty neat stuff. So let's have this top fiber class. It's going to, again, echo starting top fiber. Then when we echo this, we'll create a new fiber that will also echo some stuff. We'll get here, we'll start it. Then we'll get this output starting state nested. Then we'll suspend. Then we'll end, we'll return the nested fiber. We'll get here. And then we'll resume the nested fiber from within the outside fiber. And we'll get the ending nested. So how this looks is, when we start, we get to this point, to this echo over there. We get line 1. Then we create the nested fiber, and we start it. We start it here, and we get the echo that we get on the second line. Then, because the nested fiber will suspend, we will get here. So we'll get the third line, ending top. Then we'll return. The nested will get here. And when we resume, this is what happens. So yeah, we can play with the order of things, and this is the beauty of asynchronous programming, because you don't really know when something is going to get executed. The order is not a thing. So pretty much that's it. I think that's it. That's it. How it works. So I'm not a C programmer, so I'm not going to go into low-level details about how this works, because, yeah, I don't know. But what happens generally is, when you create a fiber, this fiber has its own stack, call stack. When the fiber gets suspended, the stack that it has gets copied somewhere in memory and gets replaced with the stack of the fiber of the previous fiber. When we resume the fiber, the same thing happens. The current stack gets copied somewhere in memory, and the stack of the fiber that is being called gets loaded, and we continue execution from where it started. And we cannot suspend the main fiber. I don't know if it's called a fiber, but we cannot suspend the top thing. The result of this is that when we debug fibers, and thanks to Derek also for that, you can actually see the execution stack of the fiber that you're debugging rather something else. For example, if you have worked with promises or callbacks, you don't get the stack of whatever coded, you get the current stack, which is somewhere. It can be at a place that has nothing to do with whatever initiated the whole sequence of things. So debugging can be hard, but because we have this call swap, stack swapping, we have a nicer debug process. So as we saw, this is really not that exciting, and as I said, fibers on their own really, you can't really do a lot. We need some more infrastructure code that needs to drive the whole process. So most probably you won't deal with fibers in your day-to-day life as developers. Most probably you'll use some sort of a asynchronous framework. A framework for asynchronous programming that will do all the boilerplate that we need in order for this to make any sense. So there are frameworks like this a lot. AMP is working on embedding fibers. Actually, the fibers are an RFC, and is something that got introduced to PHP thanks to the guys that developed the AMP framework. So what we're going to do, we're not going to talk about AMP or React PHP or anything else. We're just going to see what we need and how we can create our own little framework so that we get an idea of how we can actually use this and how this is going to be used. So we need a task. And the task that I came up with is we're going to need to download 2 files as fast as possible. So the usual way that we do it synchronously with PHP, and easiest, is like we just call file get contents, we pass in a URL, and we get the file. And then for the second file, we do the same thing. We get file, get contents. So that's super easy, plain and simple to understand. The problem is that this wastes a lot of time, and this is not really optimal. Why is this not optimal? Well, if we start downloading a file, this is something that kind of happens. So this is a timeline here on the X with some sort of time units. And here we represent when something is being downloaded. So we initiate the download, and nothing happens initially because we just wait. We wait for a connection to get established, we wait for a server response, we wait for network latency, we wait for whatever. During this wait time, we don't do anything. Our CPU is just waiting. It's wasted CPU time. And then we get some bits and pieces of information from the file, and we record them, and then we wait again. And we wait, and we wait, and we wait. And we get a little bit more file, and we continue to wait. Then a little bit more, wait, a little bit more, wait, a little bit more, wait, a little bit more. And then we get the file. And then we do the same thing for the second file, have a different graph. We get some piece of the file, we wait. We get another piece of the file, we wait. Get another piece of the file, we wait. So we have a total of 20 time units that we spent for downloading file 1. We got 12 time units for downloading file 2. This leaves us with a total time of 32 time units. Seconds, milliseconds, whatever. 32 milliseconds till we get both files. The asynchronous way to do this is to maybe not wait as much, because you see, while we wait, we can do something more meaningful than just hang around. So we can just request file 1, and then immediately after that, because, okay, we requested the file, nothing is happening, we're just waiting. And during the time we're waiting, we can request the second file. And then we can get a bit of file 1 and record it. And while waiting, maybe we can get a bit of file 2 and then record that. And then get a little bit of file 1, and then get a little bit of file 2, then get a little bit of file 1, file 2, file 2, file 1, file 1, and so on and so forth, until we get to the point where file 2 is done because it downloads faster for whatever reason, and then wait for the rest of file 1. So if we look at the graph, it will look something like this. Here we initiate both downloads. File 2 is getting downloaded while waiting. We get some pieces of file 2, so on and so forth. As you can see, there's almost no empty space here. It's constantly something is happening. File 2 gets downloaded, and then we just continue to wait for file 1. And this gives us a total time of 20 time units. Are there any, is this clear? Any questions? Okay, so how can we achieve that? Well, let's write our own function. And our own function, what it's going to do is going to open a stream socket to a client, like stream socket client. It opens the socket with a TCP connection to this URL at port 80. We got some error. We'll pass in some parameters that are regarding errors and some stuff that I can't remember. It doesn't really matter. The point is that we open the socket. We check if opening the socket was successful. We set this flag stream set blocking. This is very important to false. I'll get back to this a little later. And then fwrite, this writes to the socket, so we're going to use HTTP 1.0 simply because it's simple and we don't want to get into HTTP details. Just make an HTTP request to get the file. We're going to have a variable that is going to be an empty string content. And then we're going to have this loop, which will check FEOF. This is file. This checks whether we have reached the end of a file. So until we reach the end of the file, or the socket, until the socket gets closed, basically this is what it means, we will get some bytes from the buffer. We say 100 bytes, but it doesn't really matter how much. We'll get some bytes from the buffer. We'll concatenate them with what we've got so far, and we'll loop in here until we get all of the contents, and then we'll return the content. Is this clear? Okay, yeah. This is pretty much what file get contents does. I mean, I assume it does a little more fancy stuff, but that's it. So the important bit here is this stream set blocking. We set it to false. And this means whenever we read or write to this stream, we don't want it to block. Blocking means that when we get to df right here, if the socket is blocking, we will stay in this function until this whole string gets written to the buffer or sent, I'm not sure. Point is that we'll wait. When the stream is not blocking, we'll call this function, we'll pass it this parameter, and we'll carry on without waiting. Somewhere along the line, it will get passed over the network. We don't care. We continue our execution. Then when we read from the stream, the same thing happens. If the stream is blocking, what is going to happen is this will block until it gets 100 bytes. When the stream is not blocking, and we get to this function, it will return as many bytes there are up to 100, but it may be 20, as many bytes there are currently in the buffer. That may be nothing, that may be less than 100 bytes, that may be 100 bytes. Point is that this will not block. It will just return immediately with whatever there is in the current buffer. So those are important bits and pieces about non-blocking input and output. But it doesn't really help us much because we're still stuck in this loop. So getting there, but not really. We'll need to somehow get rid of this loop. So let's refactor a bit. If we look at this function, we can see that basically it has something resembling a start, initiation of the whole process. So this is opening the socket, setting it to non-blocking, then making the request. And then we have this loop that we need to get rid of, which is essentially reading the contents of the buffer until we receive everything. And then at the end, we return the buffer. So let's refactor this a bit in an attempt to get closer to getting rid of this while loop there. So let's create a class. In this class, we're going to have a property which will hold the content. We'll have a property which holds the file pointer to the stream, and we'll have the URL passed in. We're going to have a method start that is going to be the first block of lines that we saw. It's going to open the socket, check for errors, throw an exception, set the stream to blocking, make the request. We're going to have a function that is going to be called read some bytes, because I didn't come up with a better name, and this is what it does. It reads some bytes. And this function is going to get some bytes from the buffer and put them in the content that we're going to return. And we're going to have the isDone check, which is a function that checks whether we have reached the end of the file. And we can refactor our old function using this class, and it will look something like this. We instantiate our URL fetcher, we start it, then we still have a loop. Until the fetcher is done, we read some bytes, and then when the fetcher is done, we return the contents of the fetcher. So we still have this loop. We still cannot get rid of it, and we want to. We really want to. So the way we get rid of this loop into this function is, well, we need the loop because we need to repeat the process of reading the buffer until we read the whole thing. We just don't want it here. And what we're going to do is we're going to create a global loop. And this is this so famous or infamous, I don't know, event loop. I'm not calling this loop event loop because it has nothing to do with events. This is just a loop. And an event loop would pretty much do the same thing, but it will listen for events. The loop that an event loop does is it's looping through something that, in a loop it says like, are there any new events happening? And if there are, it handles the events in some way. So that's why it's an event loop, because it's an event. I've also heard this to be called in old Windows programming message pump, because it was not events, it was messages. So anyway, we're not going to deal with events. This is another level of complexity that is just going to make this talk harder to give. We're just going to do a loop. So this loop, what we're going to have in this loop is we're going to have an array of callbacks. Oh yeah, and this whole thing is static. Like we don't care. It's bad programming, but it's simplicity. For simplicity's sake, this is going to be static, so that it's easily accessible from the from anywhere in our application. So this is going to hold a array of callbacks. This array of callbacks is basically, we're going to use it as a first in, first out queue. We're going to have a function to add a callback on the queue of callbacks. And then we're going to have this run function, method, sorry. What we'll do is it will start iterating through the callbacks. So it'll get a callback from the beginning of the array and execute it. And it will continue doing this until the queue of callbacks is empty. And this can potentially be never. So this can be a potentially endless loop. Why? Because all of these callbacks here, they have access to the loop and they can add new stuff to the queue. So far, so good. Please, if you have any questions, don't wait for the end, just spit them out. It's all right. So we're going to get back to the URL fetcher thing. We're going to introduce a function called tick, and we're going to use the loop. Let's see what's going on here. The tick function, for lack of a better name in my head, is going to check whether we're done reading the file, and if we're done, it's going to close and call a callback that we have passed into the constructor over here. If you notice, we have a done and on error callbacks now. If we're not done, we're going to read some bytes and then add a callback to the loop here, and the callback will just call tick again. When we start, we're going to do the usual stuff. We're going to add a function to the loop that will call tick. So basically now when we start, we do all the initial stuff that we did before. We add a function on the loop that is like just called tick. Tick will be like, we'll check whether we're done reading the file. If we're done, it's going to call this callback over there, done. If it's not, it will read some bytes, and then it will add a function to call itself again. So this is how we get rid of the loop from inside. Questions? When we run the loop, this will get executed. Yeah, I said this is what we've changed. We have a done callback. We have an on error callback. We add a function to tick. We don't start looping automatically. We call the done callback once we're done. Instead of doing a loop ourselves, we just add it to the global loop. We add another call to tick. And now our function for fetching the URL will look like this. We'll add this done and on error callbacks, because our function will not return any content. What we'll do, it will just create the URL fetcher, and then it will add a start to the global loop. So now our fetch URL function pretty much does nothing except instantiating this object and adding a callback on the global loop. And it will return immediately. This is why we need the done and on error callbacks, because we have no content now. All right. Our big main function will look something like this. We'll add this big function to the loop. It will echo fetching from dir.bg. This is a site. We'll fetch the URL dir www.dir.bg. We'll add a done callback function. We'll add an error callback function. Then we'll echo fetching Google, and we'll call Google, and we'll do the same thing. And then nothing will happen until we call this final loop run, because now we just have callbacks stacked in an array. Nothing happening until we call loop run. So what happens when we call loop run? The order of execution. First, we're going to echo fetching the RBG. Then when we call fetch URL, it will return immediately. It will do some stuff, but it will return immediately. And then we get to echo fetching google.com. And then, because DRBG is faster to respond, because this is done from Bulgaria, and DRBG is Bulgarian side, and it's obviously faster to respond, we're going to get an echo got DRBG, and then, yeah, exactly, got DRBG, we echo the content that we passed, that's HTTP 1.1, moved permanently, content length, so on and so forth. And then we're going to get an echo that we got Google, and that the size of Google is 51,803 bytes. Depending on where we call them from and which responds first, the order may be switched. So yay, we got ourselves some sort of a asynchronous programming. It's a bit retarded, it's overly simplistic, but it's asynchronous. Or asynchronous, I don't really know. Anyway. The problem here is that we have those callbacks. And this can turn into the so-called callback hell, because if we depend on something that we get in a callback, if we depend on it to make a decision, this can get dirty and ugly pretty easily, because we'll have a callback. The callback will make a decision. It will probably call some other asynchronous functions. It will add other callbacks. It's ugly. And actually, I was thinking about making a more complex example, but I decided this is ugly enough. So far so bad. Bring in the fibers. How are we going to use the fibers? They're going to bring some sanity in this whole thing. More refactoring. We're going to have this f fetch URL. F stands for fibers fetch URL. And it's going to be the same, pretty much, it's going to wrap around our old function. And this is what it's going to do. First, it's going to get a reference to the current fiber that's being executed. Then it's going to call the fetch URL function as we have it now. The callbacks for done are going to be resume the fiber that we're currently in. If there is an error, throw from the fiber that we're currently in. This will put all of this hell on the loop. And then we're going to suspend the fiber. That's it. And now we're going to add a little bit of a helper function. This is let's call it a defer. This is just going to get a callable, and it will create a fiber, and then it will add a callback on the loop to start the fiber. So basically this says, execute this at some point in the time, somewhere, sometime. And now if we refactor, this is how our code is going to look. And if you notice, there are no callbacks. We're going to start fetching DRBG again, like the order becomes the same, but instead of callbacks, the DRBG variable is just going to have, we're just going to call the fetch URL from outside. There are no callbacks. We don't know that this is asynchronous. It doesn't look asynchronous. We just get the contents. We handle the exception being thrown as a normal exception. And the same goes for fetching Google. And it looks a lot nicer. So we're out of the callback hell. And this is what promises do. This is what generators with promises do. But we have now sane programming. It looks synchronous. It's not synchronous, but it looks like it is. Are we good so far? All right, great. So Let's do a quick recap of what fibers give us. So first of all, they're not intended for userland usage. Again, you need some sort of a loop, you need infrastructure, you need beautiful stuff that will help you run them. They're intended for people who will do asynchronous libraries or frameworks, the authors of those. So the benefits for the authors is that they don't get to deal with boilerplates such as promises, handling asynchronous generators, handling all this crap. They just get this for free from a fiber. For the authors and users, no asynchronous and synchronous functions. It all looks the same. The fiber function just returns as any other function. But you don't care, it just returns a value. It's like any other function. I've put red and blue in brackets there. If there is a very famous and nice article about red functions and blue functions. And it's depicting the problem that most languages have in face of having functions and asynchronous functions. And the problem with this is that if you're using an asynchronous function, if you're in asynchronous function, you can call whatever you like. But if you're if you're calling an asynchronous function, then the function that calls it needs to be asynchronous as well. So once you get to deal with asynchronous function, meaning functions that, for example, in JavaScript return promises or are labeled async, everything along the line that uses this function needs to be asynchronous as well. With PHP, with fibers, we don't get this. You don't care whether the function that you're calling is synchronous or not. You just call it, and it acts as any other function there is. This gives us the ability to, well, I've said easily on the slide, it's not going to be that easy, but that gives us the ability to refactor a synchronous input-output dealing function with an asynchronous one without having to tackle with all of the code along the line. You just refactor this particular bit and piece, which is asynchronous. You make it asynchronous. And the users, the clients of this function, they won't know, they won't care. So basically that's that. Let's compare them to generators. I've mentioned generators a couple of times because this is what we've been using to emulate or to have like asynchronous programming with PHP. So the similarities, they can both suspend themselves. Now we mentioned this already. They both suspend themselves and they both can be resumed. And they both can spit something out and get something in when they suspend and restore their execution. Now the difference is that the fibers can be suspended, as we said, anywhere from the stack. You cannot suspend a generator anywhere from the stack. The generator can suspend only itself. Nothing that the generator calls can suspend this generator. While a function that is being called somewhere, it can suspend all of the execution of all of the functions that called it. And again, fibers can be accessed anywhere from the stack. They don't need the yield keyword. This is really great because, again, this removes the need for having all, like if we have asynchronous generator, all of the users of this have to be generators. And of course, fibers cannot be iterated upon because they're not generators. And the cool fact is that when you combine them, you can get asynchronous generators. So compared to threads, so fibers are not threads. This is very important. Fibers are not threads. Fibers give us the ability to do the so-called cooperative multitasking, while threads, well, they give us the ability to use the so-called preemptive multitasking. So what does this mean? That the fibers, when you start a fiber, you rely on the code in the fiber to suspend itself, to stop its execution. The code in the fiber may decide to never do that. It's up to the programmer that it's up to you to decide whether you return the execution, you return control to something else. Because of this, it is up to the application. It's the application level that decides when and what to run. Threads, on the other hand, are switched by some sort of an external to our program mechanism. That may be the operating system or the virtual machine that we execute our code on. So, for example, the Java virtual machine or the .NET virtual machine or whatever. It's not up to us. It's not up to the programmer. It's not up to the developer of the application to decide when the thread is going to be switched. Fibers are cheaper to switch than threads. Quite frankly, I don't know why, but this is the case. Fibers execute one at a time. So when a fiber executes, this is the only thing that executes until it returns control to something else, to a higher level fiber. Nothing gets executed in parallel. Threads, on the other hand, may be executed in parallel. Now, this again depends on the virtual machine that you're using or the operating system. It depends whether you actually have a multi-core processor or if you have like a bunch of processors. If you have more than one CPU, you can actually execute code in parallel. You cannot do this with a fiber. The fiber executes one thing at a time in one thread. It's good to use fibers for input-output intensive stuff. Why? Well, because when we deal with input and output, most of the time we just wait. So while we wait, we can say like, you know, I'm going to suspend myself. I'm just going to wait here, and then something else resume me. Threads, on the other hand, are good for computationally intensive stuff. Why? Well, because they're executed in parallel. If we have multi-processor systems. If we start executing something computationally heavy in a thread, this will block the whole process. Again, nothing happens in parallel. This will block the whole process. We have to be careful. If we need to execute something computationally heavy, start it in a new process or a new thread, whatever. So basically, that's it, I do believe. And yeah, I think I covered everything. This is definitely the last slide. And if you have any questions, please, whether you do it now or find me somewhere in the halls, please, question there.
I think I'm coming. Thank you, Milko. I really enjoyed that. Got lots of questions later.
Thanks for the great presentation.
Thank you.
I have a question about, with closures, passing them into a fiber, you're passing in variables. Are those variables sort of locked in their state, or can something change them?
Ah, that's a very good question. No, well, they're locked in a state, but this is something that I meant checking yesterday. I think you cannot pass variables by reference. I may be wrong, because I forgot to check it. But yeah, they're locked in a state. Basically, this is how you would use them as a closure. There would be, well, I mean, you can modify them within the fiber. Obviously, they are not read-only variables, but none of the stuff that is happening in the fiber will leak out. Does this answer your question?
Yeah, mostly. I'm just thinking of it like from the perspective of, with a closure, you've got the use, and then you put in your variables that you're borrowing from the state and when the function was declared. And then say you pause the fiber, and then you modify those variables in the global, in the state of the calling.
Oh, yeah. It will get modified. You can still fuck up your global state. yeah. You're like, nothing helps you for that. You should be careful, yeah. You can do that. It will work, hopefully as intended. But you can do that, yeah.
Anyone else?
Hi, thanks for presentation.
Thanks.
Just want to know, like, unlike the P thread on the PHP, right? Can I assume, like, using the fiber, like, I can have the control execution, right, for the complex task? Like, on your first example, I see it, right? All the output is kind of like predicted kind of things which is going on, not like on the asynchronous kind of things, like synchronous, but programmable synchronous, asynchronous, I prefer to call it. If you just go to your first example code,
Yep.
right? The first one.
You mean the graphs, right?
The first example code which
This
you
one?
present. Not that one, that the fiber class which you
Yeah.
First
Okay.
one.
There.
Yeah, exactly. Right. Over here, right, I was assuming, right, F1 and F2 should come, right, after, sorry, it can come at any point. F1 was suspended with the
Yep.
$R1 should come at any point, but I feel like it's controlled by the programmer itself, right?
Exactly. This is exactly what's happening. It is indeed controlled by the programmer itself. Like, the programmer is in charge of scheduling and giving the order and starting and suspending the separate fibers. You're exactly right. This is absolutely true. You're in control. You should take care of this, for better or worse. The mechanism in which the fibers will get executed, the schedule, is up to the programmer. It's done in user land. It's not done by an operating system or something. It's up to the programmer to say, like, start this, stop this. Like, you start it from outside, you stop it from inside. It's your job to do it.
All right, thank you.
Yeah.
All right, someone else.
Over there.
Mostly just out of interest, because you've probably thought about this more than we have. Apart from the use case of kind of downloading files or waiting for input-output, have you got any other?
Yep. Thank you very much. Thank you very much. I was actually meaning to note this, so thank you for the question. This is a rather simple and basic example. The greater use, well, I don't know if it's a greater use case, but you can do this for any sort of input-output operation. So, for example, you can start a server. Well, when you start a server, what happens is you open a socket on your system and you wait for connections. Now, if you don't have asynchronous way of doing stuff, when you get a connection, you need to handle it, and everything else will have to wait, because you will be busy handling this connection and doing whatever it needs to get done. You wait for a request to come in, then you do the processing, and then you need to spit out the output, and then until you close the connection or whatever, everybody on the queue waits. Like, there is nothing else happening but handling this request. Now, if you do it asynchronously, you can open a socket and you can listen on the socket non-blockingly using this set stream non-blocking. You remember the function that said, yeah, this one. You set the socket to non-block it. And what you do is going to loop and like check. Are there any connections? Nope. Okay, I'll continue doing something else. Are there any, oh, there is a connection. Okay, let's open the connection. While opening the connection, which is like sending the TCP handshake or whatever, or waiting for a request to come in over this connection, you can say, okay, I opened the connection, now let's do something else. Is there something on this connection? Like, do we have a request, for example? Oh, we have a request. Okay, let's handle the request. Now you start doing some computational, some other stuff. For example, you open a connection to a database. This takes time as well. Okay, while I wait, I'm going to check on my socket. Are there any new connections happening? There are. Okay, I'll handle this while I wait for my database connection to get established. Is my database connection established? Oh, it is. Okay, let's send this query now. Until we wait for the database to figure it out, I've got to check whether something is happening on the socket that I just opened. Oh, there is another connection. Let's see what this guy wants. And so on and so forth. See, this switching between tasks, you can actually create. First thing that I can come up with is actually have a WebSocket server, for example, handling multiple connections. This is how you would do it in a single process. Of course, you need to take care of scaling, You need to take into account how much stuff you can actually do in one single process. Maybe you still need to spawn multiple processes, but you actually get to handle multiple connections without users having to wait for each other. Because in a synchronous way, you would open the connection, wait for the person on the other side to tell me what they want. Okay, I know what they want. Okay, let's open the database connection. Wait for the database connection to get established. Send the queries. Wait for the result to get back. Get the result. Send it to the user. Wait for the buffer to get flushed. Close the connection. Okay, now I can see whether somebody else wants anything. So this is the value of this whole story. Because this is like super simple, but like if I were to do a server example, we would like, fuck it. All right, thank you very much. I forgot, if you want to contact me, the usual Twitter, LinkedIn, the slides. And of course, anywhere around the venue, thank you very much again. Have a good conference.